All right. Let's wait for another minute or two and then. So, just one quick announcement. Next week is going to be the mini project presentations. So we are going to start at 2 on Friday, similar to this lecture. And probably we need until 6 p.m. to finish all the talks. So that I have time to schedule the day, please send me your talk info, basically the title of your talk and the abstract by the end of the day on Wednesday. Let's say midnight Wednesday.
Do we need to write the report, I guess?
So you don't need to send me the report by that deadline. So I sent an announcement this morning. The actual deadline for your paper, which is the report you have to write, is June 5th, if I remember correctly, or June 4th.
Is there any template or is there any plan that you are looking for?
I mean, I can share a template of kind of like what I mean by paper, a LaTeX template. Okay, sure.
Can we present our things on the board?
No, it should be a slide presentation because you only have 15 to 20 minutes.
It should be a slide.
I think it should be a slide. Is there any reason that you want to do whiteboard? Like, I can't imagine explaining anything in 15 minutes, anything substantial.
Oh, 15 minutes.
Yeah, 15 to 20, right? So you guys have twice that of that because you joined first. Well, so we will see.
You mean
How much time do you guys need?
You mean it's up to us if we think we can present our results, we can use board.
I can be flexible if this is something that you guys are interested in. But my idea was really having PowerPoint presentation so that you can practice also that style of presentation.
Oh, you prefer PowerPoint?
I definitely prefer, I mean, Beamer is fine. I mean, I prefer a slide presentation versus whiteboard presentation. And if you need more time, let me know. If, for example, you think, 30 minutes is a better fit for your project, I think I can give you that time as well. Let's put it this way. Anything between 20 to 30 minutes is acceptable. If you feel strongly about whiteboard presentation for any reason, let me know. Maybe you have a good reason and then we can figure out the solution for that. But by default, a slide presentation is preferred. Yes.
And one thing, what about the meal? Do we have meals? And like
good. So yeah, so there's gonna be, because we start at 2 p.m. it's already too late for lunch, so we are gonna have a break in the middle with coffee and pastries from Medici. So if there's anything particular you like, feel free to let me know. Otherwise, I'm just gonna get an assortment of different pastries. If anyone is allergic to coffee, then we might get chai or, I don't know, tea. You submit your order by the time that you submit your coffee. All right, so let's get started. So originally I was planning to talk about adversarially corrupted online learning today. I had a conversation with Varun, who is not actually attending today because of something that came up last minute. We decided to change the topic because, it's a very interesting paper, the one that I was planning to cover, but it's a little bit technically nuanced in the sense that I was worried that maybe you won't be able to appreciate why we are caring about that paper in just a matter of one lecture. Therefore, I decided to cover something different that is very much related to something that Varun taught last time in the previous class. So if you remember, there was one lecture about the search problem, Pandora's box problem, and how the Gittins index policy is the optimum search policy. So today I'm going to actually reteach that stuff using a slightly different notation. So there will be a lot of overlap with that lecture. If this is the first time you're attending this course, if you haven't taken the part one, I think this lecture has been designed for you. For those that they have been to part one, there is a little bit of overlap. But then the actual newest stuff I'm going to cover is the combinatorial version of the search problem. So what does that mean? Let me start with the original Pandora's box, Weitzman Pandora's box. So the problem is as followed. There are different boxes, let's say n box. Each box comes with a value drawn from a known distribution. And each box comes with an inspection cost. So I'm a searcher. My goal is to maximize the value inside one of these boxes by minimizing the cost that I'm paying for inspection. So basically my utility is going to be the value of the final box that I acquire minus the total inspection cost. And then this is capturing a lot of search scenarios in the sense that there are different options. I want to inspect these different options in order to have better information about them. And the question is, how should I devise my search strategy in order to maximize the utility of the final item that I acquire minus the total search? Now you can think about two combinatorial variants of the same problem. The combinatorial variant number one is that I'm an algorithm who is not going to only acquire one box. Maybe I can acquire a group of boxes. In particular, think of a bipartite graph where on both sides you have patients, basically donors and people, donors of kidney and people who are interested to receive kidney. And then you have to pay inspection costs for each edge to make sure how much compatible the donor and the receiver are with each other. And your goal is to basically find a matching in this graph that matches the donors to the receivers, that has the maximum total compatibility, while you are incurring the minimum inspection cost needed in order to find that match. So it's kind of a stochastic optimization problem that not everything is known upfront. There are distributional knowledge. Rather than going with the averages, going with the expectation, you're willing to pay some inspection costs to know the instance better and then do the optimization. The question is, how would you do the inspection in an adaptive fashion in order to maximize your total reward minus inspection cost? Yes.
The objective is sum of compatibilities
minus the total inspection cost that you pay. But you're forced to pick a subset of quote-unquote boxes that form a matching in a certain bipartite graph. So that's the variant number one. Variant number two, I tie your hand in your inspection. So this is a combinatorial inspection problem, meaning that you are not allowed to inspect any box. So you are only allowed to inspect a collection of boxes that, for example, they form a matching in the bipartite. And there are different reasons that the problem is interesting. So what I can mention is basically in network problems, when you try to, let's say, inspect the cost of different edges in order to find the best spanning tree that connects all the nodes together. So once you're at a node, you can only inspect edges that are connected to that node. So that means somehow the subset of edges that you inspect should form a connected subgraph. So you're not allowed to basically inspect an edge somewhere else on the graph. So because of these kinds of restrictions, the set of inspections you can have, the set of inspected elements you can have, they should all be feasible in a combinatorial sense. And the question is, given that restriction, how would you again do the search, meaning that you maximize the, let's say, value of the best box that you have inspected at the time that you stop the search minus the total inspection. But you have to be feasible in terms of inspections. So let me try to formalize these problems. I'm going to start with the original Pandora box problem. So this part is going to be very repetitive. Warren, sorry about that. I see that you have joined the call. So there is going to be a lot of repetition in this lecture. But hopefully this is going to be beneficial for those that haven't taken the previous part. We have some of those, right? How many people didn't take the previous part? 2? Okay. Did you take the previous part?
Yeah, I did.
You did. Okay, good. All right. Yes, the lecture is dedicated to
You can come back later if you want.
You're going to do some of the notation. Okay. All right, so Pandora's box problem. Just as a recap, Pandora box problem. So we have n different boxes. Each box I has some value Vi drawn from a known distribution F. So Fi's are known. And you should think of these VIs as independent random variables. Box I also has an inspection cost. Which is equal to Ci. Okay, good. So in this setting, we look at the search policy. So a search policy, let's say pi. Let me write it down informally. So this is going to be an algorithm that decides on the next box to inspect. And at some point, decides to stop. So you have to decide on the next box to inspect. And then you do this inspection. At some point, you decide to stop as the algorithm. And when you decide to stop, you have to, and then you pick one of the inspected boxes. So this is important. So for a box to be selected, it needs to be inspected. All right. So it can be also an adaptive policy. It might be a non-adaptive policy, but we are mostly interested in adaptive policies. So the goal of the searcher is to essentially maximize Vi minus summation of all the Ci's I in P. So what is I? So I is going to be defined to be the index of final selected box. And P, a subset of numbers 1 to n, is basically the set of probed or inspected boxes. And then use inspection, exploration, and probe interchangeably. So sometimes I call it probe boxes, sometimes I inspected boxes, so they are all the same. Good. So let me start by, because I think that you have seen the reservation value and the capped value concepts from previous part. Let me be a little bit quicker about that without giving a lot of intuition, just cut it to the chase. So definition, reservation value, what does that mean? So given box I, reservation value sigma I is such that is defined as follows. There is a quantity such that the expectation of Vi minus sigma I, the positive part, is equal to the cost of box I. So let's wait for a second and let me give you a little bit of intuition what does reservation value mean. Suppose I give you two offers. So offer number one, you have their reservation value, the monetary payment. You can take it and leave it. So offer number two, you have the reservation value in one of your pockets, and then you can interact with the box, pay the inspection cost, get to see the value, And after you saw the value, you're going to pick the better of the reservation value and the value. So you have the reservation value, but you also have the opportunity of interacting with the box. Now, the reservation value sigma I defined here is the one quantity that if I use as your reservation value in that two offer game, you are going to be indifferent between taking either of the offers. Let's think about it for a second. So you already have some, let's say P or let's say some R as your reservation value. If you interact with the box, the only way that is going to give you a larger benefit than R is if the value is greater than R. So then the total benefit that you get from the interaction with the box is going to be the expectation of R minus sigma I plus, the positive part of R minus sigma I. And then in order to get that benefit, you have to pay the cost CI. So therefore, your extra benefit minus cost is going to be expectation of R minus, expectation of VI minus R plus minus CI. And the moment that you become indifferent is when the reservation value is discovered. Okay. So this is kind of like the intuition about the reservation value. Is it clear? Is the two offer game clear? So on one hand, you can just stick to the reservation value. On the other hand, you have the reservation value, you can interact with the box and then pick the better of the two. And this quantity is the one reservation value that makes you indifferent between the two offers. Because the expectation of VI minus CI sigma I plus, which is how much extra you get, minus CI will be equal to 0. So you're going to be indifferent between the two options. So now, given this definition, let's do a thought experiment. Now, look at some given policy. I want to particularly highlight the fact which is going to be used later. So whether I'm going to tell you after this, I don't care whether I'm picking one box, I'm inspecting boxes from a certain feasibility environment, so on and so forth. So in what comes next, ignore any possible restrictions on set of boxes that policy pi can pick or inspect. So in the original Pandora bug problem, for the selection, you have a restriction, so you have to only select one box. And for inspection, there is really no restriction. You can inspect any subset of boxes. I'm going to talk about variants of the problem when there are going to be such restrictions. But in what comes next, which is the key lemma I'm going to show in today's lecture, all those restrictions can be simply ignored. You don't need to be worried about them. So now, back to the discussion. Let's say I pick some policy pi. I'm going to use the notation that Varun also used. So let's define a random variable AI to be the indicator that policy I selects box I. I never said this is the only box that is selected. So for the Pandora, for the Weitzman Pandora problem, there's just going to be one box. But in general, we can imagine that I'm picking a subset of boxes, and then when AI is equal to 1, that means the policy has selected that. Okay. And then we're going to define I of I to be the indicator that my policy pi inspects box I. Okay. Are the definitions clear? I take silence as a yes. So now I can write down the following. So expectation of V pi I, which is, let's say, the value that the policy pi gets, minus summation of Ci for I in the set of probes of pi, policy pi. Which, by the way, they are formed adaptive, but in an adaptive fashion, you are going to end up with some final index that you're going to pick and a subset of boxes that you're going to pick. So this, using these two random variables, can be written down as expectation of summation over all the boxes, AI times VI, minus summation over all the boxes, CI times II. And again, I haven't put any restrictions on the set of boxes I select or inspect. This equation is valid no matter what. This is just the linearity of the utility and the way that these two random errors are. Good. So now, I'm going to use the definition of the reservation value. So this quantity is going to be equal to the expectation of some I in n, AI vi minus summation I in n, I of I, and then Ci is equal to the expectation of Vi minus sigma I. All right. Now note the following. Whether I'm inspecting by box I or not as a random variable is independent from the value of that. Because the moment that you inspect, after that, the value gets realized. So that random variable has no impact on whether you inspect box I or not in an adaptive policy that doesn't see the future. Therefore, I can say, well, so the expectation of Vi minus sigma I plus times II is equal to the expectation of II times Vi minus sigma I plus. I'm just bringing out the expectation. And then I guess what I'm trying to say is that this is equal to the expectation of some I in M, AIVI. But by the way, so this is right. So this is, in fact, I'm just like replacing this term with this expectation condition II, and so because they're independent, it's going to be II times expectation of Vi minus. So it's going to be equal to II times expectation of Vi minus sigma plus conditional OMR. But because they're independent, you can drop the condition. So mathematically, I think this is what I'm trying to do. So now we can bring this expectation out, and this is just going to be sum over I in M. You will have II times Vi minus sigma I plus one expectation, and here I'm using the fact that random variable Vi is independent from I. Okay. Now we can start rewriting this in a form that gives you very interesting characterization of the value minus cost of certain class of prices. Let's do it. So we're going to look at this term. So I'm going to add AI times Vi minus sigma I plus and subtract the same thing. So I'm going to have AI times Vi minus sigma I plus, and then plus some I in N And I'm going to have AI minus II times VI minus sigma I plus. I just added and subtracted the summation of I's AI times VI minus sigma I plus to this. All right. So this quantity, the VI minus sigma I plus, is basically the minimum of VI and sigma I. And let me do a definition here. So let me call this definition 1. So I'm going to have definition 2. What I call the capped value. Capped value, sometimes called surrogate value. Surrogate value. And I have seen papers that call this virtual value. So we actually use that one too, but because we already talked about maximum virtual value, don't understand their different things. So capped value is the one that I'm going to use in the lecture. So what is capped value? So it's basically kappa I, defined to be the minimum of the value, and this deterministic quantity reservation value, which depends on the cost. And with that definition, I can say, well, so the expected value minus cost of my adaptive policy, even in a board that you are selecting more than one box and you're inspecting a certain subset of boxes with some restrictions on the selection and inspection. Even in that board, expected my total value minus total inspection cost is going to be exactly equal to the expectation of some I in n, AI times kappa I, plus some residual term, which is the expectation of some I in n, AI minus II times VI minus sigma I plus. Right? So the final observation is that this is going to be at most the first term. So this term can only be negative, simply because the only way that you can select a box is if it has been inspected before. So you cannot select an uninspected box. So AI 0.5 for any realized sample paths here is at most II. And because of that, I can say, well, so this is at most the expectation of sum of I in n, AI times kappa I. Also, we can identify the if and only if condition that we have equality. So you will have equality if and only if. Well, so each of these terms is either 0 or greater or equal than 0. So the only way that this expectation can come through is if every term is 0, pointwise. And for that to be 0, let's think about it. So if II is 0, then AI is going to be 0. Because if you have an inspected box, you cannot set for any meaningful policy, for any very physical policy. But then if II is equal to 1, you might be in two situations. Either this term is 0, which is when VI is less than or equal than sigma I, or it's not 0, VI is strictly greater than sigma I. In that case, you want AI to be 1 so that this becomes 0. So what I want is that if I inspected the box and the value of the box passed the reservation value in that VI was greater than sigma I, in that case, I have to pick the box. So if you have a policy that satisfies this condition, meaning that, again, so if you inspect the box, you get to see the value, and the value is greater than the reservation value, you're forced to pick that box. Then for your policy, this is going to be equality. Meaning that the expected value minus cost is going to be equal to the expectation of your allocations times this wiki-lucky random variable, which is the capped value. This is very interesting because now definition number 3, I'm going to define what I call the non-exposed policies. So non-exposed policy. It's a property on policies. So we say policy pi is non-exposed if it satisfies condition star, and this is condition star. So we say the policy is non-exposed if it has that property. If it inspects a box and looks at its value and the value is greater than the reservation value, then policy is forced to select that. Again, this has nothing to do with picking one box and not having any restriction on the set of inspected boxes. If I'm picking a subset of boxes and I'm restricted to pick any set of inspected boxes, but still this property is true. Okay. I mean, still everything here is valid, and if this property holds, I can say the expected value minus total cost of my policy is equal to the expected allocated capped value. This is a beautiful result. Why? Because if you give me a policy for this search problem that has inspection cost and the value that it's gonna acquire if it decides to select a box, then I don't need to be worried about its inspection at all. I can say the expected utility, the value minus cost of the policy, is equal to its expected allocated capped value, as long as it is non-exposed. And for any policy, this is a number. So I can just work with these random variables in order to find the performance of a non-exposed box. No other. Okay, good. So a bunch of simple correlates. Actually, one simple corollary. Think of any policy, no matter non-exposed or not. So the expected value of the policy minus the inspection cost consists of the expectation bi pi minus summation ci I p of pi is going to be at most expectation of the max kappa, max over I kappa. So the way I usually like to think about this, think of an instance of the profit inequality problem where your underlying random variables are these capped values. So this is the profit benchmark, the expectation max. So the profit benchmark in that instance of profit inequality will always give you an upper bound on the expected value minus cost of any adaptive policy in this search problem. Okay. And then the million-dollar question that Barnum solved in the previous lecture is, can we design a non-exposed policy that actually pointwise picks the one box that has maximum cap? So here's a question I'm going to pose. So, question. So this question pertains to the Pandora space. Then you want to pick one box and there is no restriction on inspection. So the question, can we design a policy such that it has two properties? One, it is non-exposed. What does that mean? So you design a policy in a way that every time that you inspect a box and sees the value greater than the reservation value, it is forced to pick that. So it should be non-exposed. And two, I'm asking a lot, but apparently you can do it. It's always pointwise picks the box that It's the box basically I star, which is the argmax of kappa i's. So if we can have such a policy, then this is going to be the adaptive optimum policy for sure. Is it clear, this part? So we try to have an adaptive policy such that it is non-exposed, and somehow pointwise can always pick the box that has maximum kappa. So it should be a feasible policy for the search problem. So it should, select the box, inspect the box, look at the value and do something, continue or either stop. It should be a feasible adaptive policy. But whatever it does, at the end, we want it to guarantee that it picks the one box that has maximum kappa. If that happens, and also it is non-exposed, then the expected value minus cost of your policy is going to be equal to the expected max kappa, and is an upper bound on the expected value minus cost of any adaptive policy. Therefore, this is going to be the optimal necklace. All right, and that gives us the celebrated Gittins index policy. I think this is going to be slightly different than the way that Varun wrote it down, if I remember correctly. At least the notations are slightly different. And I'm going to use this form in order to generalize it in case we have combinatorial structure. So here is the way I think about this. Okay. So if you know kappas, how would you pick the maximum kappa? The simplest greedy algorithm on the planet, right? So you have a bunch of numbers to pick the maximum. If you don't know anything about the kappas, so let's say you have no inspection power, then what would you do? So you can't inspect. You have this bunch of boxes. You try to pick the one that has maximum kappa, but you don't know. You don't have access to inspection. I don't let you to inspect. Then which box is intuitively the one that has the maximum kappa based on your current information?
The one that has maximum expected kappa.
Expected kappa, that's a good one actually. Great. Yeah, you can actually go with that because it's kind of like a profit inequality problem that you can't actually open your boxes. I'm asking the question which one you're going to pick up front, and then you're going to go with max. That's a good choice. Another way of thinking about this is that, if let's say I'm at the beginning of the algorithm when I haven't inspected. If I cannot inspect at all, I agree with you that you should go with the box with maximum expected kappa, maximum expected kappa. But another initial point that you can hope to make sense and then try to add information on top of that is actually working with sigma itself. So kind of as a rough, so kappa is always going to be smaller than sigma. It's either sigma or the value. So if I have no inspection, I'm going to replace kappa with sigma. And then, okay, so I'm going to maybe pick the box that has maximum sigma. Now I pick that box. I now have opened the box, so I can actually re-estimate these kappas. Now, rather than sigma, I calculate the value, and I re-estimate that with the actual kappa, which is the minimum of sigma and the value of the box. And then I continue. I continue until I open some box. When do I open a box? When I see a box that I have already probed. So if I see a box that I have already probed, I'm going to open that. I'm going to select that. Another way of saying is the following. So let's say I'm starting from a clock which is infinity. So each box has an upper bound that is kappa, which is sigma. So you start breaking down your clock until you hit one of these boxes. So that's going to be the box that has maximum sigma. Now that I have that box, I inspect that box, I get to see its value. If the value is above the sigma, then this is actually a good box. So it is like the one that has the maximum kappa, I'm going to pick that. Otherwise, so I'm going to replace the sigma with the value, and I'm going to start decreasing my clock. So I decrease the clock every time I hit a box that I haven't opened. I haven't probed. I'm going to probe that box. and replace its sigma with the actual kappa. And if the clock goes down and hit a box that I have already probed, then I'm going to select that box. Let me write down this operation because this way of looking at it can be easily generalized to others. So let's pick a name for that. I'm going to call it actually greedy algorithm. Greedy algorithm with partial information. So this algorithm is going to be based on some particular score. So at the beginning, let the score of each box, Ri, to be equal to sigma. All right. Now, I'm going to do the following. Pick the box I had that has the maximum arc. So I had, which is arc max of arc. Some line numbers, 1, 2. Now, line 3, if I had was already probed, select I had. And finish. If I had hasn't been probed, then set Ri, so probe the box, so probe I have, and set its score to be kappa I. So you probe I had, you get to CVI, and after you get to CVI, set the score to be kappa I, which is essentially the minimum of sigma I and Vi. And you should really think of two situations. Both of them can happen. So the first one is if the value is smaller than sigma I, in that case, you replace the score with the value. Or if the value is above the sigma I, in that case, you replace the score with the sigma. The score remains sigma I, sir. Even though the box has improved, the score is going to be sigma I. And then when you do that, go to line number 2. Is the algorithm clear? So you start with the box that has the maximum score. If the box has been already probed, you're going to select that and the process is going to finish. If you hadn't probed that box before, then you're going to probe the box, update your understanding of its kappa, meaning that you're going to look at the minimum sigma and Vi, and that would be the new score. Put it back in the set of all the boxes and go to step 2. Okay. So now we want to check both of the claims that we have here. The claim number 1, which is kind of easy. Claim 1. Greedy with partial information. So greedy with partial information algorithm is non-exposed. Does anyone know the proof? Why this is non-exposed?
The algorithm we had in previous
Which algorithm?
in previous class.
it is an algorithm previously, but from this description, it's a little bit different than Boron's description. So for example, I don't force yourself to pick an item if the value is larger than sigma. If I had a line here that if the value is greater than sigma, pick it, then it was non-exposed by definition. But this way of writing it is going to also give you a non-exposed argument.
Sorry, stupid question. In number 4, there are I is I hat, right?
Correct. It wasn't a stupid question, it was a good question. Okay, let's see what happens if vi hat is greater than sigma hat. Let's say I open a box, vi hat is strictly exponent of sigma hat. Then the score doesn't change, right? The score remains to be sigma hat, but the status of the box changes. It used to be unprobed, now it becomes probed. You go to the next iteration, the same box is going to be selected because it used to be the one that had the maximum score. The score didn't change, the score of no other box changed. So this is still going to be the box with the maximum score. But this time it is probed, so you're going to select it. So let me write down what I just said. So if vi hat is strictly greater than sigma I hat, then kappa I hat is going to be equal to sigma I hat. Therefore, same box will be picked or looked at in the next iteration. But this time it is probed. And therefore will be selected. All right. And then claim number 2 is also easy to show. Why we are actually picking the one box that has maximum kappa. I'm going to prove it in a kind of funny way because it's a proof that can be generalized. So claim number 2, the GWP algorithm picks the box and a star, which is the argmax. And just for simplicity, I think we have continuous distributions. So there will be no tie, there's just one box has the maximum kappa I. If tie happens, it doesn't matter which one you can everything work. All right, so let's think about the proof. So imagine I'm looking at this algorithm until it picks an element, it selects an element. The moment that it selects an element. Okay, so I'm running this algorithm until it selects an element. And then, okay, so up to that point, all the elements that you have inspected, you already know their kappas. So the element that you select, definitely, so the moment that you select something, everything that you have selected, it has been probed. Everything, so you have a set of problems that you haven't selected again. So all of them, they have some kappa. Okay. And then you pick the next element, so you select that one. First of all, but the fact that you're selecting an element, that means that that element has been probed already. So that element was in the set of things that you have probed. Okay. Now I claim that that element has the maximum kappa. Why is that? Because, well, for that element, its score was equal to kappa. For that element, its kappa was the largest kappa in the set of things that you have probed, because that was the one that you selected. And also, its kappa has been larger than the score of everything that hasn't been selected in that round. And for all of those, the score was equal to sigma, which is an upper bound kappa. So let me write it down. At the time, GWP selects, meaning that it's doing the final selection. Selects, let's say some I hat. What do we know? So there are a bunch of boxes that they have been opened. So you have open boxes, P. And what do we know about this set? So we know that their Ri is equal to their kappa I. And in fact, you know, even a little bit more than that, I don't want to get into details, but you know, the Ri is actually equal to their VIs, because otherwise they had been selected and you never reach this point. But let's say you know that Ri is equal to kappa I, for sure. And then there is box I hat. So there is one box in this probe box, which is I hat. Because you're selecting a box, it should definitely be a probe box. And then there are remaining boxes. So this is P. This is P complement, which are boxes that you haven't probed yet. All right. So what do I know? So I know that, well, a score of I hat is definitely greater or equal than all other scores. It is greater or equal than Ri for every I that is in P and it's not I hat. What else do I know? So I know that Ri hat is also greater or equal than Ri for every I that is in P complement. So what does this imply? So that implies that, well, so Ri hat, R of I hat is greater or equal than sigma I, because for everything that you haven't probed, their score is the original value sigma I. And sigma is always an upper bound on kappa, so therefore it's going to be greater or equal than kappa I, so you're good to go. And this quantity, you know, it is equal to kappa I hat because the box has been probed. And then for these guys, you know that R of I hat is greater or equal than their score. These are probe guys, so their score is already equal to kappa I. And again, so we know this is equal to kappa of I hat. So that means you pointwise pick the one box that has maximum kappa. Is the proof clear? So again, just to repeat the proof quickly. So looking at the moment that GWP selects a box I hat. So because it selects that box, that means that box has been probed before. Now look at the set of probe boxes and unprobed boxes. I hat is one. So we know this box at this point had the maximum score in the Gary algorithm. So that means that R of I hat was greater than Ri for every I that is probed, and R of I hat is greater than Ri for every I that is unprobed. For probed boxes, this basically means that R of I hat is greater or equal than a kappa, because everything that you probe, you replace its score with the kappa. And because I hat is probed itself, that means kappa of I hat is greater than kappa. Right? For everything that is not probed, R of I hat, its score is greater than the sigma I, because for unprobed boxes, their scores are the original score sigma I. And sigma is an upper bound on kappa. Therefore, kappa of I hat again is greater than kappa. Does it make sense?
Why are we bigger than the sigma I instead of tangent?
Why this is true?
Yeah.
Yeah, because of the greedy rule, right? So when you get to this line, you're going to pick the one box that has maximal score.
Oh, that's over all i's. Not
That's over all of
Oh,
it.
sorry.
Yeah, this is why this is. I mean, it hasn't been in the previous class, but here I'm selecting a box, changing its value, and I bring it back to the set of things that I'm exploring.
So I guess the same proof also implies if we can select k items in optimal.
Good. Excellent. So modular fact. So if you can pick this, if you let's say you can pick a subset using a greedy algorithm, and I'm going to get there. But you are almost there.
I think basically exactly the same proof.
More or less. Just wait a little bit on the rules. It doesn't literally mean that if I can solve the optimization problem using any algorithm, then I can get that as if I see. It says if I can solve the optimization problem using a class of algorithms, the greedy type algorithm, I'm going to define them formally, then the stochastic search problem will be reduced to the optimization problem. But that's going to be the next thing. Right? Is it clear? Is this thing? Good. So now back to this discussion. If you recall up to this point, I didn't use any fact related to the Pandora box, meaning that I'm picking only one box and I'm inspecting any possible set of boxes. At this point, I started using that because first I defined the benchmark in this way. That means you're only picking one box. And then second, in the way that I define that algorithm, I'm assuming that I'm picking only one element, so the algorithm has been designed based on that. So now let's try to generalize this. So how about taking a short break, maybe let's say 7 minutes, and then we will be back and talk about the generalization to matching. Right, so let's continue. Everything that you need to remember from the first part of the lecture, I tried to write it down here, in this part, in the compact fashion. So now let me explain the generalization that we are interested to solve. So this is a problem, I'm going to call it the combinatorial search. All right. So what is this problem? Suppose I have a universe of elements, which are going to denote by E. So think of E as numbers 1 to n in the previous part of the lecture. So I have a universe of elements E. And then we're going to have a feasibility environment. So F is going to be a collection of the subsets of 2 to the E. Basically a feasibility environment. So what does that mean? So we say a subset S of these elements E is going to be feasible if it is part of F. So this is going to be feasible. Otherwise, it's going to be infeasible. I'm going to add one restriction on this feasibility environment. So F is going to be So this is basically an assignment. F is downward closed. What does that mean? That means if set F is feasible and set T is a subset of F, then T is also going to be feasible. Like for example, let's say think of F as being all the elements of E, all the subsets of E that have coordinate at most K, then it's going to be downward closed, because if you have a set that has coordinate at most K, any subset of that is going to have coordinate at most K, right? Or you can think of E as being the edge sets of a graph, for example, and then F to be all the matchings, all the subsets of edges that form a matching. And then if you have a matching and you look at the subset of the matching, then the subset of the matching is going to be matching, so therefore it's going to be downward closed. Or another way, think of E as edge sets of a graph. Think of F as all the subsets that they don't form a cycle. Basically all the forest in the graph. So if you have a tree, any subset of the tree is going to also be a tree. Therefore, it's going to be downward. So these are the type of feasibility environments that we think about. Now, this is the deterministic part of the problem. On the stochastic part, actually, yeah, so we actually come here. So each element I has value vi, which is realized from the distribution fi. So again, fi's are known by the decision maker. And then we assume again each element I has an inspection cost equal to Ci. All right. So now let's think about the policy. So a search policy I, let me again write it down informally. What does it do? So the policy pi is going to observe elements by paying the inspection cost. And then at some point stops. Let P of pi to be the set of probed or inspected elements at the stopping time. Then pi is allowed to select final selection, to select subset S of pi of the probe voxels such that it's feasible. I'm going to add one more assumption here, and that's the empty set is always in F. As long as it has anything, empty set is going to fall. Here's an adaptive policy, an adaptive feasible policy for this problem. It's going to go over the elements one by one in some order that it decides on. Once it gets to an element, it's going to observe its value by paying the inspection cost. To observe the element is equivalent to seeing the value vi for the element I. So it's going to observe the elements, see their value, pay the inspection cost, and then at some point decides to stop. Then there is a set of probe boxes. So the algorithm is allowed to pick a feasible subset from the set of probe boxes. So it's not going to only pick one box or one element, it's going to pick a subset of elements. And then the goal is to maximize summation of all the values that are in the final set that it selects minus the sum of all the inspection costs that it pays. Well, let's say I'm going to maximize the expectation of this. Yes, sir.
Is there like a toy example of like, because right now we're still like in the box,
Yeah.
kind of like world, but it's kind of hard to see how that would map to like feasibility. Like
Yeah.
we have one.
Let me do one example. So, example. So I'm going to have, let's say, items on one side, and then I'm going to have agents on the other side.
Not every agent wants an item. Yeah. So
Exactly. So there is a bipartite graph. Let's say you have some edges between the agents and item. So if this is V, this is U, then I have a bipartite graph G, which is V union U and E. And it's bipartite. Then for every E in the edge set, we are thinking about D of E to be the value, let's say E equal to U1, E and U. So this is item, this is agent, the value of agent U receiving item V. So we think about an environment where each of these values is drawn from some distribution f of p. Right. So now, as a market maker, if you get to see all these values and you want to maximize the social welfare, the best thing you could do was finding a matching between the items and agents. So say the agents are unit demands. So agents are unit demands, meaning that they only need one item. And you have one item for each item type. So these are the items. So you have one unit of each item. One unit of each item. So again, back to the market making example. So if I know the value of assignment of an item to an agent for all the pairs of items and agents, and I'm a market maker, I'm going to pick a matching between the items and agents, a subset of edges that they do not intersect, so that the sum of the V's on edges on that matching is maximized. Okay, so that's the full information version of the problem, but then you don't know the values, you have only the distribution knowledge. But then you can start inspecting these edges, probing the edges, and get to see the values, but we can only do that by paying the cost. And then the question is, what will be the optimal adaptive strategy that pays these inspection costs, gets to see their values, and then at some point it stops. Say, okay, I have enough information, let's pick a matching among the probe boxes. Okay. Does that make sense? Or you can think about this side of the donors, this side the kidneys. As I mentioned at the beginning of the class, you have to pay some sort of inspection cost in order to find the compatibility between the donor and the kidney, or the donor, the donor and the receiver. So the question is, what will be the adaptive policy that optimally finds the matching that has the maximum compatibility while paying the minimum inspection cost to identify that match? Yeah, sometimes people call this kind of problem price of information. Like, how much price should you pay to obtain the amount of information that you need in order to maximize the social welfare. And there are different versions of the problem. One is the budgeted version, one is the mixed sign objective version, because we are thinking about the mixed sign objective version. Okay. All right, now back to the machinery that we developed in the first part of the class. Yes.
Isn't but and as for the notion of the price information, price of information.
Yeah.
Here we have a constraint on which couples we can at most achieve. But in that price of information, you told us what is the minimum price we should pay until we can find the maximum matching, maximum.
Let's say how much
Compatible.
inspection cost you should pay. Let's say minimum inspection cost you have to pay in order to identify a matching in the graph where the expected size of that matching, or let's say the size of that matching, is at least some certain quantity.
Yeah, but in that notion, we are maximizing the value or compatibility we have. But here we want to find a thing that maximizes the kappa, achieve that maximum.
Yeah, so we are looking at the mixed sign objective rather than budgeted version, meaning that I'm looking at the value of the final matching minus the inspection cost to identify that matching. I try to maximize such. But then for non-exposed policies, it is equivalent to finding a matching that has the maximum allocated capped value, but that's just the corollary. And my actual objective is really finding a matching by paying inspection costs that have maximum total value. That's the objective. But then you can use that trick in order to design an app. It's not that at the beginning my objective was maximizing count. I should have kept count. So kind of related to Mohammed Reza's point, so kind of a corollary. So here's what I try. Pick any policy that you would like for this problem, no matter what policy you pick. Or any policy I, and I can say the expectation of VI for all i's that are in the final selection set, which is going to be feasible, so it's one of the feasible sets, minus the sum of the inspection cost. So this quantity is going to be at most the expectations of what I call summation AI capital I in N. So how do I define I in, sorry, E? How do I define AI? So AI is the indicator that the policy I selects element I. And in particular, this quantity is definitely at most the expectation of the following offline optimization problem. The profit inequality problem subject to feasibility constraint, where each random variable is replaced with a capped value. In mathematical language, not the gibberish language, so we are trying to maximize summation of xi capital I, subject to vector x is, let's say, a 0, 1 to the e vector that is feasible. So think about a full information problem where the, for example, for the matching case, where the weight of each edge, sum over all the edges. So where the weight of each edge is equal to the capped value for this distribution. Okay, so it's the full information. I know the exact realization. Then I find the maximum weight matching. For example, in this example. In general, you maximize this linear objective subject to picking one feasible substance, where the weight of each element is equal to kappa. And I take the expectation at the end. So I claim this is true. Why? So we already proved that, right? Because we proved this line and we know that this is going to be equality if the policy is not exposed. And then AIs is 0, 1 random variables for every realization will give you a feasible set. So therefore, this is going to be osmosis. Is it clear? It's kind of at the level of mandate. There's really no interesting proof going on here. So this one we already proved, because if you remember, when we were using the capped value and when we introduced that, at that point, as I highlighted, we didn't need to have any restriction on how the AIs and IIs, the inspection random variables and allocation random variables are generated. So you could have maybe a constraint like this on the selection, or maybe you can even have a constraint on inspection. So no matter what, this inequality is true. Is it clear? Do you want me to explain? Because if you're interested, another way of writing this down is saying that expectation of summation I in E, AI VI minus summation I in E, II CI, and then the rest of the calculation will give you exactly this upper bound. And we know that this is going to be equality if the policy is not exposed. What is a non-exposed policy in this language? Every time that you inspect an element, if the value of the element is strictly greater than the reservation value, you have to pick that element. So we know this is at most equal to that, and it is equal for non-exposed. And then why this is upper bounded by this quantity? Well, so it's a feasible policy. If you look at the vector AI, the selection vector, I'm going to have some zeros for some of the edges, some 1 for another set of edges. But I know that the set of edges that have a 1 form a matching, for example, in this case. And the weight of each edge is equal to the kappa, the capped value of that edge. Therefore, it's going to be upper bounded by the max weight matching points by points for each realization. And therefore, in expectation, this is also true. Yes, Colin.
In the previous simple case, by chance, we had an algorithm that fixed the maximum cap. It was really completely, I think, by chance.
It's not completely by chance. In fact, greedy algorithm in matrix finds the maximum weight basis. We were just working with one uniform matrix in a very special case. Yes.
Okay, but I mean, in general settings, if we find somehow a notion of the power of policies, some notion of, then we can get the union of that, the sets that can choose from, those policies can choose from, I mean the intersection of that set, and also that if
you continue for another 5 seconds, I'm going to say, let's take it off.
Okay. No, I mean, no, it's less than 5 seconds. The intersection with if.
5 seconds now, let's get offline. So, but I'm going to try to kind of like formalize some of the ideas you have, meaning that maybe I can use some algorithm for the offline optimization problem, the one that you know the kappas, and then transform those algorithms into policies for the stochastic probing problem. Sorry, the stochastic selection problem, the combinatorial search problem. Let me introduce greedy algorithms.
Oh, can you please not erase the office?
I'm not going to erase that. Sure. Okay, so let's define what I call frugal or greedy type algorithms. So what are these algorithms? What's the optimization problem they try to solve? Consider the selection problem over the feasibility environment F, where you have a weight for each element. Okay, so let me write down the setting, and then I write the algorithm, and then you see what I'm trying to say. So suppose for each element E, we have a weight. Let's call that WE. Element E, or element I, we have a weight. Let's call that WI. Okay. Now, consider a collection of set functions, collection of set functions. So I'm going to have for every set S, you should think of it as a subset of the elements. I'm defining GS of W S and WI and I. Okay, so let me parse this function. So we start with this weight. Right. And then given these weights, I'm going to define a bunch of functions for each subset S, G of S, WS, WI, and I. So you should think of it as, suppose I have a subset of elements S, and I'm looking at a new element to be added to this set. How much marginal gain do I get by adding that? That's the interpretation, the abstract interpretation. So I'm going to call them consider collection of subsets, define these functions. So I'm going to call them the marginal gain functions. And they have the property that for every S, for every W, the GS of WS and W and I, so this is the marginal gain of element I, is monotone increasing in WI. Meaning that if I have selected a subset of elements in some sense with some given weights, I'm looking at a new element I to be added with weights WI. If I increase that weight, the marginal gain is going to go up. And marginal gain at this point is a very abstract object. Gain is also abstract. Okay. So now, given these functions, I'm going to design an algorithm that basically will try to solve the problem, which is maximization of, so it's going to be basically the problem in which you're trying to find a set in that feasibility environment that has the maximum total weights. So let me write it down here. So the goal try to an algorithm that finds S in F such that summation of WI in S is maximized. So it's going to find a set S that is feasible, and summation of I in S is maximus. Let me give you an example let me actually tell you what the algorithm is, and then I'm going to give you an example. So a frugal algorithm with function G. So adding G is going to be the frugal or the greedy type algorithm with function G or function class G. Function class G. So the input to the greedy type algorithm is going to be a weight. So add G with weights W is defined in the following way. So, right, so we are gonna step one. Let M to be the empty set. So you're gonna start with the empty set. Step two. Find the element I had, which is equal to, actually let me something better. For every element I that is not in M, computes a score, which is going to be the marginal gain of that element if it is added to M using G function. So Ri is going to be equal to G of M, given the origin weights, but only for subset M. So I didn't define this notation. So this notation is basically all the Wi's I in S. So it's all the W's for subset M. So we're going to look at GWM and then WI for that particular vertex and I. So it's going to define the score. Then pick. The pick is a bit different from select. So it's not finalizing the session. So just pick the element I had, which is the one that maximizes or I among all the I's that are not in M. So among all the remaining elements, I'm going to pick the one that has the maximum score. Okay. So if M union I is feasible, then add this element to I. So I'm going to add I to my set. Otherwise, return M and finish and terminate. So I'm going to see whether adding this element is going to maintain my set feasible. So you start from empty set, so it is feasible at the beginning. So you pick the first element that has the maximum marginal gain, you add it to the set, and double check whether adding that element is going to maintain feasibility. So if you remain feasible, you are going to continue. Otherwise, you're going to return the M and terminate. So if you get to this line, then go to line 2. So you only get to this line if you haven't terminated. And in this way, you're going to end up with a feasible set. All right. Just some very trivial so just some, before that, let me actually make a little bit of modification to make my life easier. So I'm gonna look at the class of function G's. So let me add an assumption basically on function G. So assumption I'm gonna say the GM of any WM, WI and I is gonna be equal to minus infinity, the smallest number you can imagine, if M union I is not feasible. To kind of like force myself to never pick an element that is making the set infeasible, I'm gonna let the marginal gain of that element be minus infinity. Therefore, in this step, under this assumption, I could say rather than if M union I is feasible, I could say equivalently, if Ri was not equal to minus infinity, meaning that the element that I picked is not one of those that has the negative infinity gain. So if you add this assumption to G, and if the element that you are adding is making set M infeasible, then G becomes negative infinity. So rather than checking whether M union I is feasible, you could alternatively check whether Ri is minus infinity or not. If Ri is not equal to minus infinity, then adding this element is not causing you trouble in terms of feasibility. Then do that, otherwise you can whatever. So just like notation. So if you saw me saying that, hey, Ri was negative infinity, that is essentially meaning that adding the element is making you infeasible. Yes.
What do you mean by monotone increasing in WI?
You will see in a second why.
Actually, yes, can we discuss the function J in like a bit more details?
Yep.
Like,
Let me give you an example.
yeah. that
So let
would
me
be
give you a couple of examples. Let me give you a couple of examples to make things super clear. So example number 1. Let's call it K uniform matroid, which is the gibberish word for K selection. K is not capitalized K. So this is a matroid order. This is basically a feasibility environment where we say the set S is feasible if the cardinality of the set is at most K. Okay, so here's a greedy algorithm for this environment. So I define G of M, W, M, Wi, and I to be essentially equal to Wi if cardinality of M is at most K minus 1. Meaning that if the previous set has at most K minus 1 elements, if I add this set, the marginal gain is going to be equal to Wi. Otherwise, the marginal gain is going to be minus infinity because you make the set infinity.
And we got rid of the notion of like inspection costs.
At this point, yeah, this is pure optimization problem. When you have weights and you want to pick a subset that is feasible with its maximum total.
And we're assuming all weights are positive, right?
For now, let's say they're positive.
Wait.
Even if they are not positive, it's not going to cause me any problem. Because I mean, this is just some right. So
Can I ask a question?
Yeah.
Does I belong, does Wi, is Wi an element of the vector Wm?
if W of is an element of the vector W. No, so think of W as a vector in R plus to the E for now.
So basically, E is all possible options, and Wm is a vector which has non-zero elements in M set.
So Wm is a vector in R plus to the power M,
Okay.
so which is basically so W.
Oh, so we do not
M,
necessarily need
I
I to be
equals-
inside M.
We don't necessarily I is actually not in. So the way to think about that is I is not in M.
Oh, I.
So it's like I
right.
have selected a bunch of elements M. I'm looking at a new element I that I want to add to M. And then the gain is going to be WI. I can technically add the element, otherwise it's going to be 0. So this is just defining some algorithm. And then if you run this algorithm, it is going to pick the set that has coordinates at most k with the maximum W. It's going to pick the top WI, top k WI. So the greedy algorithm with this function is going to pick the top k elements.
WI are fixed numbers, yeah?
For now,
From
they
the
think of
beginning.
as 6 numbers. And let's say they're positive so that we won't have the issue with positive.
But for later, if they can depend on each other. So the monotone increasing function, are you taking the partial derivative or?
Just wait a minute. It's just monotone increasing, meaning that if I fix WS and I look at I, if I increase WI, then this function increases. That's the meaning of monotone increasing in WI. Everything else fixed, if you increase WI, then this is going to go. Next, we have question. So it's just like a simple example. For the maximum matching problem, you can also define the same thing. So imagine I have these different edges. I define the G of a matching, and the matching that I have currently preserved, WM, WI, and I to get equal to the weight. If adding the edge I to matching M maintains the set to still be a matching. So let me so for matching in bipartite graphs. I'm going to define G of M, W, M, WI, and I to be equal to WI if M union I is a matching. Otherwise, I'm going to let it to be minus. And then if, for example, we have negative W's, the way that we redefine the function G is that if M is at most k minus 1 and WI was greater or equal than 0, then it's going to be equal to WI. Otherwise, it's going to be equal to minus infinity. So that I never pick any element that has negative W. And same here. So you can always modify these functions in a way that you, for this problem, pick the optimal set. And what do we pick in this problem if we run this greedy algorithm? So I run the greedy algorithm, this greedy algorithm, it's going to give me a subset of the edges. How far that can be from the maximum weight function.
Is it two approximations?
Yeah, so this gives me a 2 approximation for the maximum weight function. And the reason to see that it can be as bad as a 2 approximation. Imagine this is my bipartite graph. So this is one side. This is another side. So this is 1 plus epsilon. This is 1, this is 1. So this greedy algorithm is going to pick this edge. Because it's the one that has the maximum edge. Now that it picked this, it can never pick this or that because G function, the marginal gain for this edge is going to be negative infinity, for this edge is going to be negative infinity, so it never picks these 2 edges. So the greedy algorithm gets 1 plus epsilon. But then there was a matching, which is this one, that has weight 2. So this algorithm can be as bad as a 2 approximation. And in fact, it is always a 2 approximation. Let me just show you a simple proof. It's kind of by induction, a simple charging argument. So every time that this algorithm picks an edge, let's say greedy picks edge E, right? So there is one edge W that the greedy picks. in the bipartite case. You have one side here, the other side. So two cases. The case one, W is actually one edge in the maximum weighted match. In that case, you're good to go because you picked exactly the same edge that the optimum would have. Case number two, let's say WE is not in opt. Then I claim that there will be at most two edges in opt that you cannot pick because of the selection of this edge. And then the remaining edges of opt are things that you can probably pick at the later stages of the opt. In fact, when you think about this edge, there might be at most two edges, essentially this edge and this edge. And there will be no more than two edges because opt is a match. So there will be two edges of opt, WE1 opt and WE2 opt that you could, that because of the selection of this edge, you can never pick. But here's the funny fact. So WE, because you could pick WE, so you can say WE is greater or equal than this edge, this weight, and WE is greater or equal than this weight.
What if there is an edge above the red one? You pick that first.
Right. So, so in that case, there will be just one edge in the opt that you could. So basically, this edge. Well, so I think what I'm trying to say is that given the subset of edges that you have picked, there are at most two edges in opt that you could potentially pick in this system. So and let's say these are the two edges that. So if, for example, you have picked this edge earlier, then this edge is not something that you can pick in this stage. I'm just looking at all of the edges in the optimum solution that you can possibly pick in this stage. And there are those two of them. And you're better than most of them. So therefore, you can say the amount of damage that you cause to opt is the sum of these two, but then you gain at least half of that damage.
So I guess we are considering the first time your algorithm deviates from the optimal.
Right.
So
I mean, yes and no. I mean, I'm doing a. You can think of like an induction argument, or you can think of a step-by-step argument. Both work. So if you feel better with the induction, let's say up to this point, I have always picked an edge that is for opt. Let's say I'm looking at, as you said, the first time that I pick an edge that doesn't belong to opt. Now, there are these two certain edges that I can never pick in future in the optimum solution. And then the gain that I have, I'm going to charge it to, basically, I'm going to charge these two edges in the optimum solution to this gain that I gain. And the sum of the two is going to, divided by 2, is going to be at most the gain that I get. So therefore, half of the loss to optimum solution will be gained by the algorithm. And you continue this argument and you show that always how much you gain is going to be at least how much you cause damage to opt divided by 2. That gives you a half approximation. Okay. So I didn't want to go through the details of the proof, but this is kind of like a proof, a sketch that why a greedy algorithm will give you a half approximation. There are other problems in which the greedy algorithm will actually give you the exact optimum solution. One example is when the elements are the edges of a graph, and then F is defined to be the subset of edges that they don't form a cycle. All the facts. Then if you sort the edges based on their weights and you start adding them until the first time that you have a cycle, then the tree that you end up with is going to be maximum weighted time tree. This algorithm is known by the name of Kruskal, and the reason that it can find is kind of like similar. You can do a charging argument, or there is an exchange argument. I don't want to go through those details, but for those that are curious, there is a generalization of all those feasibility environments called a matrix, such that the greedy algorithm will find the maximum weight feasible solution exactly. And if you look at the intersection of two matrices, which is actually matching, then you can get a two approximation. If you have intersection of k matrices, the greedy algorithm will give you a k plus one approximation. These are essentially how the greedy algorithm will perform in different feasibility environments. But for the purpose of this class, I don't want to focus on any of those. Let's assume I have access to a greedy algorithm that will give me some alpha approximation. Alpha might be 1, for example, in the k selection problem, alpha might be 2, like in the matching problem, or alpha might be, again, 1 for selecting a tree. But I don't care about that number, let's keep it as a parameter. So what we are going to show is that given access to such an algorithm, we can solve the combinatorial search problem matching exactly the same approximation. This time, we are going to compare the expected value minus inspection cost of our algorithm versus the expected value minus the inspection cost of the optimal online price. That's one.
For the intersection of k matrix, shouldn't it be k approximate?
No, so if k is equal to 1, then for intersection of two matrices, you're going to get, right, for intersection of k matrices, you're going to get k approximation. For basically, right, k plus L, for L system, you get L plus 1. And intersection of two matrices is a 1 system. Right. For intersection of k matrix, we get k approximation. Matching is intersection of two partition matrices. And it's a very good result. There is a generalization of matrix called L systems. That's like too much abstract. Matrix by itself is pretty much very abstract. Anyways, so the assumption I'm going to work with is not that we have a matrix environment or matching environment or any other specific environment. What we are going to work with is that actually. Yeah, I think I can erase the algorithm. Can I erase this part of my question? Right, so here is basically the way we think about the problem. Let me write down a proposition. So proposition. So given any downward close with the utility environment F and any frugal or greedy type frugal or greedy type algorithm and G, so it is endowed with some function. So given any feasibility environment and any frugal algorithm alg G, there exists an adaptive policy high for the combinatorial search problem. Such that One, I is non-exposed. Two, this policy pointwise is returning the same set as the frugal algorithm when the original weights of the frugal algorithm are the cap factors. So I return the same set as G when the original weights are the cap factors. And just as a reminder, for capital I is the minimum of VI and C. Let's try to parse this theorem because I think that's the most important part. So remember at the beginning of the class, so we talked about this trivial greedy algorithm that picks the maximum value in your set, right? When in a set of universe 1 to n, the greedy algorithm picks the maximum value. So the one trivial algorithm that we started with. And then given that algorithm, we came up with an adaptive search policy that was not exposed. And pointwise was picking the one item that the greedy algorithm was returning, the item that had the maximum kappa. So we are generalizing that proposition. So this is the right generalization. So given a downward closed environment F and any greedy type algorithm endowed with the function G, we are going to show that there exists adaptive policy such that, first of all, for the combinatorial search, such that it is not exposed. This part, we already know the definition, meaning that if at some point during the inspection process, the policy observes a value that passes the reservation value, it's going to pick it for sure. Second, it always returns exactly the same set as if you had run the frugal or greedy type algorithm when the weights were kappas. For example, in the matching problem, imagine that you assign a number to each edge equal to the capped value of that edge, and you run the maximum weight matching. Not the maximum. So you run the greedy algorithm on the graph. So the greedy algorithm will give you some matching. I claim that there is an adaptive policy that in the search problem can return a matching that is exactly the one matching that the greedy algorithm on kappas on the cap values return. I think parsing this theory is probably like the most important part. Just understanding what does it say, because the proof is quite similar to the thing that we have seen so far. Let me try to actually parse the theorem in a different way. So I'm looking at two different books. So the combinatorial search. So this is word number one, and then the other word is the full information optimization problem. I want to make sure that you understand this picture because it is probably the most important part I want to teach. So we have the combinatorial search with values and inspection costs, and then we have the full information optimization in which you want to just pick a set that has the maximum weights, and it is feasible. So here, our benchmark is the optimum online policy pi that returns set of probed elements P and S of pi as a set of selected elements in pi such that this is feasible, S of pi is feasible, and expectation of sum of VI, i.e. S of pi minus sum of Ci, i.e. P of pi is maximum. So that's the optimum online policy as a benchmark. Here we have a different benchmark. So we're looking at the benchmark in this problem. So here I set the weights to be equal to kappas. So Wi is going to be equal to kappa I, which is equal to the minimum of Vi and sigma I. And I assume everything is full information, so I know all these random variables. So my benchmark is basically the set S that is feasible, such that I'm maximizing summation of xi vi for every I in S, where S is feasible. Using the set S, which is equal to argmax. So this is the benchmark. So the one benchmark of not the so the benchmark that maximizes summation x by ki, I. Then we have the greedy algorithm here. When you run the greedy algorithm with G function, the weights are kappa, so it's going to return some set. And now here we are going to have a greedy search policy. I haven't told you what that policy is. So the greedy search policy, we're going to fill this gap, what this policy is. But whatever it does, based on this theorem, this greedy search policy, which is one adaptive policy, is going to pointwise return the same set as the greedy algorithm when the weights are kept.
So,
And it is non-exposed, yes.
so the greedy search policy in this like online environment is going to give us the same result as the greedy algorithm in the full information like setting.
Because it is non-exposed, right? So basically, it returns the same set as this guy. Therefore, the expected kappa, so the expected allocated kappa of this policy will be exactly equal to the expected allocated kappa of this policy. And then it is not exposed, so the expected allocated kappa here will be equal to the expected value minus inspection cost.
Mm-hmm.
Putting these two pieces together, the expected value minus cost of this policy will be equal to the expected kappa of the greedy algorithm. And then, if you know that the expected kappa of the greedy algorithm is, let's say, alpha times the expected maximum kappa, then that means the expected value minus cost of this policy is at least alpha times the expected maximum kappa in this setting. Maximum kappa is always an upper bound on the optimum online policy. Therefore, this search policy is going to be alpha. So the only thing that I need to show is basically this proposition, that there is a non-exposed policy that returns the same set as the other. Yes.
If we're doing the probability algorithm, then what weights are we taking? Because you said it returns the same set as the same algorithm on K.
Right.
But it's a bit of a tautology, no? Because like in the proposition,
Mhm.
what weights are we taking initially?
I haven't told you how to design this policy. So this is going to be some adaptive policy, which I will have to write next. But what I'm saying is, run a thought experiment in which you run the greedy algorithm with weights equal to kappa. That is going to return some S. Whatever policy I'm going to write down next is going to return exactly the same. And then because of the fact that it is non-exposed, we can say the expected value minus cost of the search policy is going to be equal to the expected allocated kappa it gets. And because it returns the same set, it's going to be the expected allocated kappa of this algorithm. So therefore, if this algorithm has been designed to be doing the getting an alpha approximation for this optimization, full information optimization problem, then that alpha approximation carries over to the search problem, which is quite cool. All right. So let me write down this corollary, and then I'm going to show you corollary. If and G of K is an alpha approximation for the full information problem. What does that mean? That means, let's say, for every realization of the kappa, we kind of know summation of kappa I so we know summation of kappa I in the set returned by this algorithm is greater or equal than alpha times the optimum solution. So it's max over summation, max over all x's that are in 0, 1 to the n. X is feasible. And I'm looking at the linear function summation I in 0, 1 to the e, sorry, I in e x I kappa I. So this is just a fancy way of writing down the set that has the maximum total Weitzman kappa. So if this is true for every kappa, then the adaptive policy from proposition 2, let's call this proposition 2. I don't know if this is 2 or 1. Actually, it's proposition 1. I don't think we have any proposition. Proposition 1. So then the adaptive policy from proposition Y is alpha approximation of optimal online search function. Let me show you the proof. So we say let's call this adaptive policy ALG. So we say the expected, actually this is pi, right? So we use pi for this. So expectation of summation V of pi, I in the set selected by the policy pi minus the cost for all the elements that are probed by pi is equal to expectation of AI, kappa I, for all I in E. So what is AI? So AI, as always, is equal to the indicator that policy pi selects element I. And this is equal because policy pi is non-express. And then because of proposition 1, we know this policy exactly returns the same set as the one that is selected by the greedy algorithm. So this is going to be equal to expectation of summation kappa I for every single I that is in the frugal algorithm when the weights are kappa. And then because we know it is an alpha approximation, so this is because of the approximation guarantee of G in full information problem. So this is greater we call the expectation of max over all x's in F, summation over all I E, x I kappa I times alpha. It's alpha approximation. And then we know for any adaptive policy for the search problem, this quantity is going to be an upper bound. We already established that. So this is going to be greater than alpha times expectation of, let's say, summation I in SF I star minus summation I in probe of pi star, where the pi star is the optimal search place. Okay, so in the lecture, in this lecture, we basically showed every single step. For example, let's focus on one of the examples, the matching example. So for the matching example, we know alpha is equal to 2. We showed this step. We showed this step. So this is because I forgot what was the name of the lemma. So the capped value theorem. It's called the capped value theorem. Except this is. So the only thing that we need to show is that there is an adaptive policy that is non-exposed, that proposition, and that point by point, for every realization kappa will give you the same set that is returned by the gradient. And if we show that, then we're done. Yes.
Don't we have to input the G functions to the frugal gradient equation?
That goes into this part. So you have to design G in a way that this alpha is a large number.
But G is not in our hand. You said that any frugal gradient algorithm.
Right.
So it has its own G.
Sure.
But we only input the weights to it.
Correct. Yeah. So this is part of the input. So the input to this problem is the feasibility environment, some frugal algorithm with a given G. Now, given these two, I'm going to design this adaptive policy that works and has the property one. And then, so you kind of like reduce the combinatorial search to an optimization problem. After you have the reduction, now you need to design this G that has the monotonicity structure and has the best approximation factor you can. For example, the greedy algorithm for the maximum weight matching gives you a 2 approximation. This is actually the best thing you can hope for using any greedy algorithm. I'm not going to show you that, but this is the case. And yeah, it's kind of like a design. So yeah, so it's a reduction from the price of information problem to the optimization. So I'm getting rid of the stochastic probing aspect of the problem and the cost that you have to pay for inspection, and just say, hey, try to solve the optimization problem using a greedy algorithm. If you can do that and you can get some approximation factor, then approximation factor will carry over to the search problem, which is quite powerful. Okay, good. The only remaining part is showing this adaptive policy. If you don't need this part of the whiteboard, I'm going to erase it. this point. And this is not going to be complicated. This is just like a adaptation of the previous Gittins index policy that we had. And the proof is one line. Once I write on the algorithm, we'll see everything is very clear. So the greedy adaptive combinatorial search. Let's call it GCSA. So here's how it works. Step one, let's start from the empty set. So M is going to be the empty set. So I'm going to maintain a score for every element. So the score at the beginning is just going to be the reservation value. And as you start inspecting, you update the reservation value with their count size, similar to the previous algorithm, the Gittins index policy. So step number 2, let Ri to be equal to sigma I for every element I in. All right. And actually, let me use a different one. So I'm gonna let Wi to be sigma I. Sorry about that. So Wi is gonna be sigma I for every I in E because I use R for the rank in the greedy algorithm. Now, for each element, I in E, actually, this is for every element for each element I not in M, compute Ri, which is going to be equal to the G function given set M, the current W's for the M, Wi, whatever it is, and I. After you compute these numbers, then pick the next element that has the maximum margin. Then pick I hat that maximizes Ri for every I that is not in. So number 4, if I hat is not probed, then probe I hat as always. So if I had is not probed, I'm going to probe that element. And when I probe the element, I'm going to update the weight. So I'm going to set the weights to be equal to now the capped value. It used to be sigma I, now that I inspect, I'm going to replace it with the capped value. So it's going to be equal to essentially the minimum of the value that you observe for I hat, minimum bi hat, and sigma I hat. All right. Now, if I hat was probed, is already probed. And somehow the marginal gain is not minus infinity, meaning that so
A quick question. I guess the feasibility does not depend on the weights.
the feasibility does not depend on the weights. Yeah.
So if Ri is not negative infinity at the beginning, it won't be negative infinity here.
Right. Yeah. So if it was not negative infinity, it's not going to be negative infinity here as well. But these two cases are disjunct. So this is for the case that I hat is not probed. This is for the case that I hat is already probed. So after you compute Ri, either you go to 4 or 5, depending on the case. And here, if adding I makes it invisible, then Ri is going to be negative infinity. If it is not, then adding I is not making you invisible. Did I answer your question?
Yeah, but I guess we can check the invisibility as step 3 directly. If no one feasible, we just quit. That's fine.
Yeah, that's true.
They are
So
equivalent.
I totally agree. So if you compute, yes, you could terminate here as well. But I'm not going to do the termination here. So you really the thing. Yeah. So if I terminate here, then I'm not going to probe the things that I will never select. So I think my algorithm is a little bit inefficient in the sense that, if, for example, here R is negative infinity, that means no element in future can be added to my set. But then if it is not probed, I'm going to still probe it. You see, I'm going to still probe it.
Even if it's negative infinity.
Right, even if it's negative infinity. But it's never going to be added. So next step I'm going to check. Your version is slightly more efficient. If I had is already probed and R is not equal to negative infinity, then that means, well, so it's a kind of element that you want to add to your set. Then update M with I. So you see, this is kind of following the frugal algorithm. So that frugal algorithm is saying that, hey, pick the guy with the maximum Ri. If Ri is negative infinity, then terminate. If it is not negative infinity, then add it to the set. So I'm kind of doing the same thing. But adding this intermediate step that if the element wasn't probed, I'm not adding it to the set. I'm just going to probe it and update the weight with the cap. This is the only line that is different from the frugal. So okay, so if it's already probed, then what? But if Ri is negative infinity, meaning that, well, so no element can be essentially added to your set. The maximum one has R equal to negative infinity. That means all the elements they have are negative infinity. So no future element can be added to your set, then terminate. Terminate and return. Let me actually write it down in a separate line, it's more clear. If R of I hat and if I hat was equal to negative infinity, then return M and terminate. Otherwise, go to step 3. And that's interrupt. So thinking about the matching example, for example. So I sort all the edges at the beginning based on the reservation values, the original deterministic numbers of them. Then I pick the first edge that has the maximum reservation value. I inspect that edge. It gives me some value. If the value is greater than the sigma, I'm going to pick that edge. If the value is smaller than sigma, then I'm going to look at the second edge that I can add to the match. Yes.
In the Frugal algorithm, we needed to know WI.
Right. And in step 2, I'm actually having the initial WI for this.
Okay. But we never updated WI in the, we just
do. So
added
if you inspect this element, so the moment that you add it, the moment it gets selected, this I hat, then if it's not probed, you're going to update WI. If it is already probed, you're going to pick it, if you can. Otherwise, you're going to try it.
No, my problem is in the Frugal algorithm,
Yeah.
we input WI to it, and you said we input kappa to it.
Mhm.
So we say we know kappa from the beginning,
Sure.
and we give kappa. But first of all, you are computing function g on sigma, not kappa.
Sure.
The first, and the second point, after that you are.
You have a different W. Weights. So for this algorithm, somehow, I guess what you're saying is that here I'm running the Frugal algorithm inside, but I'm changing the weights of the Frugal algorithm.
So it's not a Frugal algorithm.
It's not
because
Frugal.
the argmax is not the argmax that Frugal is gonna change.
Correct. I mean, yes, so I'm not using the Frugal algorithm in a black box fashion. I'm doing an update that is similar to the one that Frugal algorithm is doing.
Okay.
It's similar to the one that Frugal algorithm is doing. The only difference is that Frugal algorithm starts with the correct weights, kappas at the beginning. I gradually update my kappas.
WM, in other words, WM is same with the Frugal algorithm, but
Exactly.
WI
This
is.
is different.
Yeah.
But then I'm going to show that I'm actually picking exactly the same element as in the Frugal algorithm. Basically, I'm going to show this algorithm is going to return the same set, and this is when I'm using the monotonicity of G.
And I'm guessing the costs are incorporated into this G function, or
the cost. So here, you're absolutely right that I didn't talk about it, because the costs are incorporated in the kappas. This is the way to think about it. But I'm basically guaranteeing only bullet 1 and bullet 2. Here, I never mention anything related to the cost. Why? Because I know that if the policy is not exposed, then the expected value minus cost is going to be equal to the expected allocated capital or capped value. So it's kind of integrated into cost. Honestly, I think this reminds me of the Myers-Briggs virtual value function, if you remember. So in the virtual value world, when we were thinking about maximizing revenue, we could say, you can forget about the prices, the payment rule, and just look at the allocation rule. And if you look at the allocated virtual value, that automatically for any Bayesian incentive compatible mechanism is going to be equal to the expected payment from that agent. Here, replace the incentive compatibility with non-exposure. And the virtual value with the capped value is exactly the same thing.
It's also like UCB, like you mentioned the upper bound for WI.
Yeah. KLUCB. So let's start to prove the two claims. The first one, claim number 1, this is non-exposed. Yeah, I think in the interest of time, I probably won't get to the conventional inspection Simon, because this is the part that I want to cover for you. Monarch is working on its questions related to search and fairness, and somehow last week we realized it is related to combinatorial inspection, and very selfishly I decided to change this lecture to cover this material for Mohammed and myself. But karma, so I'm not going to get to that. But let's actually finish the lecture with this group.
Quick question. Here, this taking the min between the value of the sigma is just kind of a way of the cap standard decision that like, oh, we'll only pick it if it's above reservation value. That's like kind of
right. So what would happen if the value is above the reservation value.
Yeah, you like recycle it and then
So you prove my claim. So claim one, let's follow Pepe's proof. So claim one, pi is non-exposed. So proof, let me say it in words and then I'm gonna write it down. This is exactly what Pepe mentioned. So we get one iteration of this algorithm. At some point, let's say you get to see a value that passes the reservation value. So you get to see a value that is greater than the reservation. What would you do? So previously, the score of that element, the weight, was equal to sigma, and it was unprobed. Now the value is greater than the reservation value. What is the kappa?
Previous version.
The reservation value is. So the kappa doesn't change after you do this update. So if this, and now the element, the unprobed element becomes probed. Okay, so if it used to be the best element to consider, it's going to remain best element to consider. So I consider that element, but this time its status has changed from unprobed to probed, so you're going to add it to your set. Okay. Excellent. Yeah, and I now think I should change the algorithm a little bit based on Chen's intuition actually, because good. So here I have to check whether I hat, if I hat is not probed. Yeah, okay, good. Let me change the algorithm a little bit. I'm going to explain why. It was very subtle. We pick this I hat if R of I hat is negative infinity, terminate and return M. Otherwise, continue. Otherwise, it's going to automatically continue. Now here, I don't need to be worried about that because I know this is not the case. If R hat is equal to the determinant return M, if it is not probed, then do this. If it is probed, then add it without even being worried that this is going to make it invisible, because it's not. And if you get to this point, that means you should just go to a step. Go to a step 3. Yeah, let me now explain what happened. So in the previous version, there was a chance that, let's say you pick the best element. You cannot add it because R is equal to negative infinity. Now you go and inspect it. And now it turns out that VI is greater than sigma I. So you are forced to pick such an element. So you're going to cycle it back to your algorithm. But then next time you realize that, wow, the Ri was negative infinity. So I couldn't add, I can't add that algorithm. And then you're going to violate the non-exclusion. Here, when I do the check here, let's see what happens. So if you probe the element and somehow you realize that, well, so this element is something that makes me infeasible, then I terminate. I only get to inspect the element if adding the element is possible. And then if adding the element is possible, if I inspect that, and it turns out the value is greater than the reservation value, the kappa is going to now be equal to the reservation value, you cycle it back. The next iteration, you pick exactly the same element, but this time its status has changed from not probed to probed, therefore you select.
The only difference is one inspection cost, yeah.
Yeah. So
You
the only,
had feasibility in that as well.
right, I mean, you lose the non-exposure in that sense, because, no, I mean, in the previous iteration, in the previous version, I might select an infeasible element and inspect that element. And then VI turns out to be larger than sigma I.
Yeah.
Right?
We want to close our eyes, not see the, by not inspecting, we want to escape from the exposure.
Right. Yeah. Yeah, at the beginning it turned out to me that this version is a little bit more efficient, but it's actually necessary. Is it clear why this is necessary?
Yes, only the last one that.
Right. Yeah, because again, if you inspect something that is infeasible and it turns out to pass the reservation value, either you lose non-exposure or you are going to have an infeasible element by one, an infeasible set by one element. So you want both of them to not happen, so therefore you have to change it. So you have to check the infeasibility right after you look at your candidate to be added. If the candidate is an infeasible candidate, just terminate and return the set. Great. So to say the proof, consider a time when GCSP inspects an element I hat and V of I hat is greater than sigma I. If that happens, then W of I hat becomes kappa of I hat, which is equal to the minimum of V of I hat and sigma of I hat, so it's going to be equal to sigma I hat. But now I hat is a probed element. In the next iteration, the algorithm again takes I hat as sigma I hat, which is equal to, right, so yeah, because its the score hasn't changed, as our I hat and all other RIs have not changed. So none of these RIs have changed. And this time, sub x I hat, meaning that it's going to be added to. So therefore, it is not. All right, good. So now let's think about the claim number 2. It's not that harder. Claim number 2. So this policy returns the same set as G when it's run with weights cap. So look at the first, so imagine that I run 2 parallel algorithms, so one, and I couple them together. So one is going to be the frugal algorithm on actual realizations of capital. And then the other one is going to be my algorithm, and every time that I inspect, I use the capital that has been used in the run of the frugal. So this is kind of a coupling the 2 runs. Now look at the first time that these 2 algorithms pick a different element. So proof. Consider running and GK on actual realization, realizations of V or cap. So in your head, imagine you first sample from all these elements. These are going to be the randomness that is going to define your sample path. Now run the frugal algorithm on K. And then run the other algorithm. Consider the first time that the two algorithms they select, and by select I don't mean the probing, the actual selection. That let's say GCSP selects an element I and let's say this arg G selects something that selects J which is not equal to. Let's see what happens, what can go wrong. Right, so
They're not at the same time clock, yeah?
so the first time, what I mean is basically up to this point, they have selected exactly the same sense.
Yeah, I mean they're not at the same iteration.
No, not the same iteration. No.
Yeah.
I'm running this algorithm, I'm running the other algorithm, so they are evolving to sets of selected elements. And you look at this evolution, the first time that the prefixes, so look at the longest common prefixes in these two sets.
And then the next one.
Now look at the moment when this algorithm, the GCSP selects the next element.
And also the moment that the other one. Because the moment is not same.
No, it's not.
Do you lose anything by just assuming that you run greedy first and then you run GCSP?
I run the greedy first.
And then you kind of like just look at what greedy's doing.
You can do that. Let's say I run the greedy up front and I know this set. Good. Maybe that's even better. I like that. So I run the greedy first. That gives me a complete set. Now I run that algorithm. I look at the first time that I'm adding an element that is not the right element in the sequence, exact same sequence generated in the set. Okay. So basically, the first time that the set of my elements has a different prefix than the other set. Good. So let's see what happened in that moment. Right. I guess what I want to argue is that, well, so up to this point, the two algorithms, they have the same set. So M is the common set of selected and probed by the other algorithm, probed elements. By, let's say, GCSP. Okay. So everyone here has already been probed. So their weights are replaced with their capped values. Now, let's look at the G of M. When I look at the WM, kappa I. Is that what I'm going to do? Actually, kappa J. Yes. So kappa J and J. So I'm looking at this experiment where I have both algorithms that have selected set M. I'm considering adding element J with weight kappa J. So this is the margin of that field. Okay. So now this is at most the GM of WM, actually sigma J and J. Why is that? Because G is a monotone function. So G is monotonic, increasing in second argument. And we know by definition of kappa J is always smaller than sigma J. Is either sigma J or the value. All right. Now, J is not the element that has been picked by the algorithm. In fact, algorithm selects I. And now here's one thing that you should consider. So this only happens if J is an unprobed element. Because if J was a probed element, then the kappa was then okay. So because algorithm select I is a probed element. If J was a probed element, then you have two kappas that they are competing with each other. Because when you probe an element, you replace the score with the kappa. So if you selected the one that has the maximum kappa, then the frugal algorithm should have selected the one with the maximum kappa, because this is what the frugal algorithm. So again, what I'm trying to say is that if you encounter in this situation, then definitely we can imply just from this that I is a probed element and J is unprobed element. The fact that the algorithm selects element I means that I should have been probed by that. Otherwise, you don't select an element that is unprobed. First, why J is unprobed? Because if J was probed, then your algorithm would have selected J. You know, J is the one that is picked in the frugal algorithm. So frugal is picking the one that has the maximum kappa and can be added to your set. But if J was already probed, you would have selected J instead of I. So the fact that your algorithm picked I, that means J should be unprobed. So J is unprobed, I is probed. Now, well, so from the perspective of I, J was unprobed, so this was a score of J at the time. And you decided to pick I, who was a probed element. That means the score of I was larger than the score of J. So that means this was at most GM of WM. What is the score of I? I is a probed element, so the score is equal to its kappa. So it's going to be kappa I and I. All right. So this is true because of the monotonicity of G. This is true because of so many things. So one, I is probed. And therefore, because I is probed, we can say R of I is equal to kappa I. Second, J is unprobed. And because of that, you can say the score of J is equal to sigma J. And third, because algorithm picks the element I over J, that means Ri has been, let's say, greater than Rj. I'm going to change this around. Let's say there will be no ties to just make our life easier. So the algorithm picks I over J because Ri was greater than Rj. And now you see the contradiction. Why? Because, well, so why did frugal algorithm pick J over I while the score of the I was greater than J? So that's going to be a contradiction. Because GM of WM, KI and I should be greater or equal than GM of WM, KJ and J, simply because J is picked by L G under J. And that finishes it. All right. That's it. So basically, we are going to pick exactly the same set as the gradient. And this policy is also going to be non-exposed. Therefore, the expected value minus cost now is going to be expected allocated kappa, which is expected allocated kappa of the greedy algorithm, which is alpha approximation to the expected maximum allocated kappa, which is at least alpha times the expected value minus cost of the option one policy. And that gives us a proof.
Should we consider also the cases that if it stops sooner or later, there is no J? I mean,
What do you mean by that?
like,
Oh, you mean
one case is our algorithm until now has select all the things that the frugal has chosen, but now has also choose another thing on top of that, or
yeah, I
vice
guess
versa.
yeah, so I guess think about the following. So let's say yeah, you should consider that, but it will be automatically captured by the same proof, because somehow when that happens, so the only case I need to consider is when the GCSP hasn't terminated, but the frugal has terminated.
And vice
Yeah,
versa.
and there's also vice versa, there's also the case when something is equal, like when GM.
Yeah, so that's when I can keep by just saying that, hey, let's say no type can happen. And if type happens, then you can say, change the decision of the frugal algorithm to actually pick the other element, right? So
Are we not allowed to like pick all of them before we reach our class?
so here's what I'm going to do. So I'm going to say, if there is a type, then pick the one set that is following the frugal group and has the maximum similarity with the one that is shipped by the frugal.
And what is one combination for another?
Yeah.
Actually, doesn't, like by definition, for the greedy algorithm to be an approximation, it should work regardless